Catalysis is an incredibly important thing in chemistry. In industrial chemistry, it's important because it's how you manage to make things affordably by finding conditions where you can make reactions happen without needing ludicrous amounts of energy and things like that. It's important in the lab for making reactions happen that would just be impossibly slow otherwise, and it's hugely important in biology because enzymes, which are what control everything to do with life pretty much, they do that by acting as selective catalysts for reactions. So catalysis is something we need to know about, and we need to be able to explain it in various ways. So first of all, there's the sort of definition which you need, which is that a catalyst increases the rate of reaction without itself being used up. So it's different from a reactant. Now we're going to add to that in a minute by explaining how we did it, but let's look at that in terms of the enthalpy profile diagram first. So if we have enthalpy up here, we have reactants and the products. If this is an exothermic reaction, it's going to look like that. So that's delta H, which is the overall enthalpy change of reaction. And the important thing to say first of all is that that is not changed by the catalyst. Okay, so the enthalpy change of reaction is what it is, and the catalyst has no bearing on that. What the catalyst does do is change the activation energy. So remember, activation energy has to do with this. The idea that in order to get from reactants to products, you have to go over an energy barrier first and then down the other side. And the size of that energy barrier is what controls the rate of reaction, because the higher it is, the lower the probability that particles will have enough energy to react when they collide. So this is the activation energy, and that's the all-important thing for rates of reaction. So you can see what a catalyst needs to do to make the reaction go quicker is to change the height of that activation energy. Can't change the energies of the starting state, but it can change the height of that hill. So what we can do is say, right, well, here's an alternative pathway. Okay, it starts and finishes in the same place, but now this is the activation energy with the catalyst. And that's the key idea for what catalysts do. So we can add that into this general statement at the top, that the catalyst increases the rate of reaction without itself being used up, and it does that by providing an alternative reaction pathway, so this hill rather than that one, with a lower activation energy. Okay, so that's the general statement that you need to have ready to make. So that's a really important sentence that you need to use to describe what a catalyst does. The diagram is also important if they ask you to explain it in terms of an enthalpy profile diagram. That's what that diagram is. And just make it clear. I think bringing these arrows for the activation energy out to the side like that, rather than drawing them in there, makes it much clearer. So that's a good thing to practice. And of course the other thing we can do is relate this to what's going on with the Boltzmann distribution. So let's have a look at that. So here's our Boltzmann distribution. So we've got number of molecules here, and energy along the bottom. And here's our curve. And as we've discussed, that curve is a function of the temperature, but it doesn't change for anything else. It doesn't change if you change the concentration, nor does it change if you put a catalyst in there. So that's really important. The curve stays the same, but what changes is the activation energy. So if that is the activation energy, remember we just mark it on as a vertical line like that, and then shade in the area like that. Say, right, here's the activation energy, and just explain that that is equivalent to the population of molecules with energy greater than the activation energy in the absence of a catalyst. And now, of course, you can see what's going to happen. That when you put the catalyst in, the curve doesn't change, but the activation energy does. So now we'll have a new activation energy, which is smaller. So this is activation energy prime, in other words, with the catalyst. And you can see the difference it makes is that now we have this huge area representing the population with enough energy to react when they collide. And that tells you why the rate is faster. That the molecules don't collide any more frequently, but when they collide, they have a much higher probability of having enough energy to react. And therefore the rate is increased. Okay, so we can just put that label on there as well. That this is the population with energy greater than EA prime in the presence of a catalyst. Okay, so you can see how powerful the idea of activation energy is, that we've used it in conjunction with the Boltzmann distribution to explain what temperature does, but also what a catalyst does. So again, we just need to be able to put that into words. So we already have this general statement about what catalysts do: increase the rate of reaction without themselves being used up by providing an alternative reaction pathway with a lower activation energy, and you know, that's what the diagram shows too. So all you really need to add to that is to bring in this language of successful collisions, because that's what this is all about. So you say alternative reaction pathway with lower activation energy, thereby increasing the frequency of successful collisions. That word frequency is important there. People tend to say increasing the number of successful collisions, and examiners tend to get all pedantic then and say, well, the number of successful collisions is however many you want it to be, you just have to wait as long as it takes. So, you know, they're being awkward there and saying, well, it's not the number, it's how many you get in a given time. So frequency is a good way of saying that. Now, if we think of a couple of examples of catalysis from the chemistry that you've already come across, one of them is, for example, in the hydrogenation of a alkene. So if we have ethene, you know that it can react with hydrogen gas to make ethane. So that's an addition reaction, and you just learnt the condition for that was that you had a nickel catalyst. Now that sort of catalyst is called a heterogeneous catalyst. So that's a word you need to know. And what it means is that it's in a different phase from the actual reactants involved, because this is a gas and this is a gas. Okay, so these are mixed up together in the gas phase, but this is a solid. And that's what heterogeneous catalyst is. The definition is just that it's a catalyst which is in a different phase from the reactant. But what that usually means is that it's a solid, or occasionally a liquid, and the catalysis happens on the surface of the solid. So in that case, it's when these molecules land on the surface of the solid that their interactions with the nickel atoms in the metal basically weaken the bonding somewhat in the molecule, and that's what lowers the activation energy. But you don't need to know that story, you just need to know the word. So heterogeneous catalyst is usually a solid, could be a liquid, but the definition is that it's in a different phase from the reactants. You have also come across an example of a homogeneous catalyst which is in the same phase as the reactant, and that was Cl dot, the chlorine atom, in the decomposition of ozone. Because remember, the reaction was this, O3, which is a gas, plus chlorine radical, also in the gas phase, gives you ClO dot plus O2. And then, just to remind you, the other bit of that cycle is that ClO dot plus an oxygen atom. All of this in the gas phase then gives you regenerated Cl dot plus another O2. So overall, you can see that the chlorine atoms cancel out because they're used up in the first step but regenerated in the second step. And that's a classic example of how catalysis works. That it's not that the catalyst isn't involved in the reaction, it very much is. You can see that it reacts, but then it gets regenerated. So overall, it's not used up. And therefore the overall equation for that, once you cancel out the chlorines and also the ClO intermediate, is that you get O3 plus O goes to 2O2, is the overall reaction. So the Cl dot's not involved overall, but that doesn't mean it's not involved, it's just not used up because it's used up but then regenerated. And that's an example of a homogeneous catalyst, because it's in the same phase as the reactants. So again, make sure you know the words, and it's worth knowing those examples. You'll come across other examples, you've already come across some other ones, but it's worth having a couple of examples like that up your sleeve. So final thing to say about catalysis is, because it is such an important topic, they do sometimes ask you to explain, why it matters so much, and the answer they want tends to be about industrial catalysis, so not about enzymes and things like that. You and I might think that's the coolest example of catalysis, but in a chemistry exam it tends to be focused on industrial chemistry. So there are really a couple of issues. One is that it can reduce your costs, because basically it allows reactions to be carried out at lower temperature, because obviously by speeding up the reaction using a catalyst, you don't have to speed it up by raising the temperature, and that really has two benefits. So you get reduced fuel costs, but also you get less pollution, greenhouse gases and so on. From burning fuel, so it's environmentally advantageous as well as being economically a good thing. So that's the first thing. The other thing, which is perhaps slightly less obvious than that, but it's very important, is that it allows different reactions to be used. Which may be more sustainable, or again also cheaper. So the idea is that some possible ways of making products may just be ruled out normally just because they require extreme conditions. So they might be favourable in terms of using cheaply available raw materials, having a high atom economy so that you don't produce lots of waste materials. But if you need to go to extreme conditions to make them happen at a reasonable rate, that may just rule them out as being realistic. But by using a catalyst, the conditions may become then accessible. Now, the classic example of that is ammonia. So ammonia is made today, and has been really for about a century, by direct reaction of nitrogen and hydrogen. Before that, it was made by a much more complicated chemical process with a much lower atom economy. It was very wasteful, but you had to do it that way because the direct reaction of nitrogen and hydrogen was just so slow at any reasonable temperature that you just couldn't make it happen. Once a catalyst was discovered that could make that reaction feasible, it was a massive leap forward, because you could make ammonia then much more cheaply and with much less waste and so on. So this idea of allowing the possibility of different reactions that would otherwise be inaccessible is very important. And as people are trying to improve sustainability, which means produce less waste, use up less of our finite resources, the search for new catalysts is a very important part of that.